and welcome back to Aussie's Young Learning Emporium. In today's video, I'm trying to do a little bit of a crash course in calculus basics. So this is all about differentiation, and this is part 1 of differentiation. There are going to be some questions that I'm going to do in the next video, which can help you prepare for an exam, it's just like a revision for you really, because I'm going to go over the fundamentals but not too much into like complicated questions, but the basics will be clear by the end of this video, and you will be able to attempt those hard questions with the concept that you've got, and you should be able to do it. It might require a bit of more effort, but we can practice some more of those questions in the next video, which is going to be part 2. But in this video, we're just focusing on the basics, on the formula, on all of the other things like finding the formula of the tangent and all of that. So let's get into this video. To start with, we've got the differentiation formula. First of all, let's just think about what really is differentiation. What differentiation tells us is basically what is the gradient. We're trying to find the gradient of like a curve like this one at any point, right? So we can make like a gradient line. So this line, for example, over here can show us how the gradient for this curve changes. So we can talk about at x is equal to this much, the gradient of this curve is this. So whatever is like the y value of this is going to be the gradient of this curve at x is equal to that much, okay? So basically, what differentiation really is doing is, if I just clean it up a little bit, I'll go to the side and show you. So let's see, this is our curve, and we want to find the gradient, which is basically like the slope of the curve. So at any point, if we made like a line touching exactly that point, this is called a tangent, by the way. So we're trying to find out what would be the slope, what would be like, kind of like you can think about it how tilted it is at that point, and that would be the gradient. So we're trying to find the gradient of this curve. Now, since it is a curve, the gradient is always changing. The tangent is always going to change how much it's bent. It keeps on changing, right? So basically, when we draw the gradient function, let's say over here the gradient is about like -4, so maybe it's here, and then over here maybe the gradient is about, let's say, +4, so maybe it's over here. So now the line for the gradient is going to look a little bit like this, assuming that this is actually connected. That wasn't really good on my side, but yeah, this is basically what differentiation is trying to do. So if this is fx, which is basically a function of x, so it's basically when we did like y is equal to x square, we can just write fx, which is a function of x, is equal to x square. So here y is equal to fx, so that's basically, we just write it as fx. It's a bit more fancy, nicer. So we can just say this is f dash of x. So this is a function of x, this curve, and this is f dash of x. So the derivative function of x, okay? Now, let's go back over here. I'll just rub this out so that it's a bit cleaner for us. Cool. So now, the formula for this is actually this one. So fx is equal to x to the power of n, which is f dash is equal to nx minus n to the n minus 1. So basically what this really means is that if a function of x looks a bit like this, x to the power of n, when you differentiate it, this power, this exponent is going to come over here, and you're just going to take away 1 from the exponent, all right? So what I'm really going to get into now is the definition of the derivative and how we got this formula. All right, so you can skip ahead. I have put some time markings in this description, so you can skip ahead if you want to skip ahead to the actual basics. But here I'm just going to show you how this formula came to be and what is really the story behind it. Not really the story, but the mathematical reasoning behind it. So we're trying to find the slope or the gradient of a point on this curve, all right? So obviously we can just go ahead and do our normal stuff. So the gradient of this curve should be y2 minus y1 over x2 minus x1, because that's how it is for a line, right? That's the formula of the gradient. So let's say that we have got our function. So we've got fx. This is fx over here. All right. This function, this curve is fx, and basically we're going to take another point really close to fx. Basically, this is any point on the curve. And now we're going to take another point quite close to it. And basically, what this has happened is that, okay, I'm going to take some more space and show you. What has happened is that if this is x, we're just talking about the x coordinate, then we have added some length, and let's say that's h. So this point, the x coordinate would be x plus h over here, and that is what has happened over here. And since our x has changed, in our function, instead of fx, it's now going to be fx plus h, because our variable, if it was x squared, that was our initial function, then now it is x plus h squared at this point, right? So that's why we're going to write fx plus h for the y coordinate over here. Let me just erase this for a bit real quick. What's not letting me do more? I'll just rub this out then. Cool. Now, what we're going to do now is we're going to use a thing called limit. What limit really does is limit is a way to say that something is infinitely close to something else. So let's say A is really, really close to B, but it isn't equal to B. All right, so here we're going to use limit. H is tending towards 0. H is almost 0, but it isn't quite 0 yet. You know why? Because we want these points to get infinitely close, but we obviously can't make it the same, otherwise you can't really do, this will become, this derivation, this gradient would become 0 over 0, and that wouldn't really work out. So what you're really doing over here is trying to get these points really, really close to each other. That's our goal over here, and that's what we're doing. So now that h is almost 0, what this means for us is now that these points are really close. So if we found the gradient between these points, the gradient that is made at these two, like if we connect these points, this would make like a line, and if they were infinitely close, then that would mean it's almost basically the gradient of that point. So now we can go ahead and write this out. So we've got fx plus h, which is y2, minus fx, which is y1, divided by x plus h, which is x2, minus x. And when we simplify this, we get this. All right. Now, we can write it as this. So f dash of x is, we're going to write this limit just to make sure our that we know that h is almost 0, but not quite. And this is how we can write it up. This is our derivation. So f dash is equal to limit h tending towards 0, fx plus h minus fx over h. So that is basically how we came to this much. Now, to get it into our formula, which is this one, how do we do it? Here is when we're going to use the binomial theorem. So let's say fx is equal to x to the power of n. All right. So now if we look back at our fx over here is equal to x plus h, this one, this bit over here. So this becomes f x plus h. So if we're doing fx is equal to x to the power of n, then fx plus h is equal to x plus h to the power of n, right? So that's what I've done over here. This is what I've written over here. Cool. I'll just rub this out. Now, so the binomial theorem is basically about expanding expressions like these. A plus b to the power of 0, that is 1. A plus b to the power of 2, that is a squared plus b squared plus 2ab. A plus b to the power of 3, that is going to be painful. But what about a plus b to the 20, right? To the power of 20. How do we work that out? Now here is where the binomial theorem comes in. The theorem basically says that a plus b to the power of n, any number, take n as any number, alright, is gonna be equal to this. They're a little bit complicated, but not too complicated. Let me explain. So, we're saying, let's take an example actually. Let's say a plus b to the power of 4 is what we're trying to find out. So we're going to start with this little bit. This is basically the sum. We call this sigma. This basically represents sum in mathematics. So we're saying that we're going to take the sum of k to until it equals n. Okay, until k equals n, we're going to keep adding this with each other. Alright, so what are we adding with each other? We're adding n, choose k, a to the n minus k, b to the k, which is equal to, so basically the n choose k, what does this really mean? This means basically n to n factorial divided by k factorial in brackets n minus k factorial. If you have seen my video previously, this is actually the combination formula. And why this really presents itself in the binomial theorem is because basically this theorem works because the coefficients of the terms in each binomial expansion of an expression of the form a plus b to the n to the power of n matches the numbers on Pascal's triangle. And the cool thing is that these numbers in this triangle can be formed using the combinations formula. Pascal's triangle is basically a triangle where we add like the top two stuff and we get the bottom stuff. So basically, if we had, I can't really remember how it looks like, but we basically have 1, 1, 1, 1, 2, maybe 1 again, and then we get 1, 3, 3, 1, and this is how it just keeps going, right? So what this is, if I keep going, this becomes 1, 4, 6, 4, 1. Okay, keep looking at this. Now we're gonna expand a plus b to the 4, right? So we're gonna do this combinations thingy thing, and we're gonna get 4, choose 0, a to the 4, plus 4, choose 1, a to the 3, b to the 1, and so on. And if we simplify this, what we get is a squared plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4. Now look at the coefficients. It goes, here is 1, 4, 6, 4, and then this is 1 because there's nothing. Look at the Pascal's triangle. We get 1, 4, 6, 4, 1. And that is so cool. That is how, where this really came from. Now, let me just rub this out real quick. Now, from here, we're going to prove that the differentiation formula really came from whatever this thing was. Okay, let's prove it. Okay, so we're gonna expand it. Since we had x plus h to the power of n, we're gonna expand it, and what we're really gonna get is x to the n plus nx to the n minus 1 h plus n, and then you keep going on and on. But what we can instantly do from here is that we've got x to the n to start with and x to the n to finish with. And since we have got these two, and this is negative x to the power of n and this is positive, then we can cancel those out instantly, right? So the x to the n terms cancel each other out. Now we divide each term by h, because we have h at the bottom. So what we do is to kind of single it out. So first we've got n x to the n minus 1 h over h, and over here h cancels out, and that's what we keep doing for each term in there. All right, so when we do that, we remove this let me grab the pen, we remove this h essentially. So that's why we've got nx nx to the n minus 1 is what we've got at the beginning of it. Where were we? Okay, cool. So now we're gonna keep going on and dot dot dot. Now, since we said basically the next h term is h squared, so it becomes just h. So let me just put the iPad over here. So what this really means, if we now we know that h is approaching 0, right? And now if we want to cancel the h, we want to get rid of the h, we can basically go back to our thing that we said that all of it is basically 0. So now we can just assume, since it's infinitely close to 0, let's just say it's 0, okay? And since h multiplies each term from here on, all of the other ones after this has h in it, what happens is that since you're multiplying by 0, all of the terms become 0. And that's why the equation becomes if dash x is equal to nx to the n minus 1. And that is why this is really cool, this proof. Anyways, so this is how this formula kind of came to be. Now let's look at some questions real quick. So we want to differentiate if x is equal to x cubed. We use our formula, which is f dash x is equal to nx to the n minus 1. So f dash x becomes 3 comes to the front, and we do 3 minus 1, so it becomes 3x squared. Does that kind of make sense? I hope it does. Then we want to find the equation of the gradient. So the equation of the gradient will be this. So for this function, the equation of the gradient at each point, there's a cubic, so it won't look like that. It would look a bit more like this, right? So this is going to be the formula for the gradient, which is gonna be over here. Where were we? Okay, cool. And if we want to find the gradient at x is equal to 2 for this one, what we can do is we're going to use a method called substitution. Okay, so we're going to say f dash x is equal to 3x squared. We know that. But what if we replace x with 2? Because that's what we're doing. We're substituting 2 for x. So we've got f dash 2, and we're going to replace x by 2 since we're substituting. And we get 3 times 2 squared, which is 3 times 4. This is a multiplication, by the way, that dot. All right, and that is equal to 12. So the gradient at x is equal to 2 is 12. Pretty self-explanatory, pretty simple for now. So now, if we're trying to differentiate if x is equal to 1 by x. Now, since x is in the denominator, if you think back to our algebra classes, what this means is that x is basically to the power of -1, because it's basically anytime it's like 1 by x, it's basically equal to x to the power of -1. If it was x2 in the denominator, then it's x to the power of -2, and so on, right? So since we know that it is in the denominator, this is let me grab the pen. This is x to the power of -1, and I don't know why this keeps doing this. It's really annoying. But this becomes -x because the -1 comes in front, and to the power of -2. All right. Now, this we can basically write as -1 by x squared. Also the same thing, because it's negative, and then since it's x to the power of -2, it's basically 1 by x squared, right? Now, if we want to differentiate if x is equal to 1 over 3x squared, now again, what we can do is to take out the x squared and bring it up. We can basically write 1 by 3x squared is equal to 1/3 times x to the power of -2. Same thing, all right? That's what I've done over here. I've written it out like that, and then when we differentiate it, all that happens is that this -2 comes in the front and it becomes -2/3, and x is left with, basically this becomes -1, so now x has an exponent of -3, and if we write it out again as a fraction, it becomes -2/3x cubed. Pretty cool so far, I think. If you have got any questions, pop them down in the comment section below, but let's move on. So now if we're trying to find the coordinates where gradient is a specific number. Okay, so take this example. Y is equal to x squared minus 2x minus 5, and it has a gradient of 6. At what coordinate will it have the gradient of 6? Cool, so we're going to do dy by dx, which is basically differentiating. There's basically f dash x is equal to that. Or if you don't want to use dy by dx, and if it's something like the a, right, area is equal to x squared or something, then when you differentiate it, it can just become a dash is equal to x squared. So that also works. All right. So getting back into this, we differentiated, the 2 comes in front, becomes 2x. Because we have 1 as the exponent over here, when it comes to the front, it just remains -2. So anytime x has a power of 1 over here, or it has no power that you can see, then the number in front of it, when it gets differentiated, the x goes away and the number remains, and that's all that remains, okay? So and now we know that this is equal to 6, so we can solve this like a normal, that would be a normal equation from here. So we can go 2x minus 2 is equal to 6, so 2x is equal to 4. That should be equal to 8, That should be equal to 8, and because when we send this 2 to the other side, it becomes +2. So 2x is equal to 8 and x is equal to 4. Sorry about that mistake, but yeah, that's how we can just go about this if we want to find the x value. So since we know that x is equal to 2 at this point, now we just have to find the y. So we're going to put it back into this first equation, and we have got y is equal to, so since x is equal to 2, we're substituting. So anywhere there was an x, we're going to replace it with a 2. So we've got 2 squared minus 2 times 2 minus 5. So this becomes 4. That wasn't really the answer. So let's just do plugging x is equal to 4 into the calculation instead. So we've got y is equal to 4 squared minus 2 times 4 minus 5. So this becomes 16 minus 8 minus 5, and that becomes 3. Cool. So the answer is actually not going to be that. It's actually going to be 4 and it was 3. That is the answer. Sorry about that little mistake. But yeah, this is how you can find the coordinates for a point. Like, we want to find the point where the gradient is equal to 6, and this is how we can do it. All right, so moving on to some more questions. Find the coordinates where the gradient is 0 for the curve y is equal to x minus 1/3 of x cubed. This is actually a cubic, so it is going to look a bit like this. So anytime it's a cubic, we know that there's going to be 2 turning points. These points here and here, these are called turning points. All right, these are called turning points. And in a quadratic, which is basically when it's like x to the power of 2, since this is the highest power on x is 3 over here, it's a cubic. Here it's 2, so this is a quadratic, and it just has 1 turning point. All right, so let me just rub this out. Cool. So 2 points where gradient is equal to 0. So at turning points, as you can see, the gradient is 0 because there is no slope, no angle to it. All right, so dy by dx over here is going to be equal to 1, since this is a lone x, no like other exponent, not 2, just 1. So obviously it's going to turn into the constant coefficient, which is 1 minus x squared, because when this 3 comes to the front, it becomes 3 by 3x squared, and that is basically equal to 1x squared, but it was a negative, as we can see over here. So that's what it becomes over here. And now we're saying that the gradient is equal to 0. So now we're just going to factorize it from here. So when we factorize 1 minus x squared, it becomes x plus 1, x minus 1, and that is equal to 0. So that means that x is equal to 1 and x is equal to minus 1 are solutions to this equation. So now we're going to plug in x values back into the initial equation. So for x is equal to 1, this becomes y is equal to 1 minus 1/3, 1 cubed, so that becomes 2/3. And for x is equal to minus 1, it becomes y is equal to minus 1 plus 1/3, which is equal to minus 2/3. So these are the coordinates over here, and that is how we can find the coordinates for a point where there is a given gradient. All right. Now, these are also what we called maxima and the minima. Also something really important to note over here, okay? So the maxima is basically the maximum point, pretty self-explanatory, right? And the minima is the lowest point before it goes into infinity on both sides, all right? So here for this example, the maxima is going to be 1 and 2/3, because obviously if you look on the x-axis, if this is the graph of that equation that we have to start with, then obviously when there is a 1, this is gonna be the maxima, because if this is minus 1, this is 1. If you think about the x-axis, then obviously minus 1 comes before 1, so that's why this point has to be our minus 1, 1, which is gonna be our minima, and this one is our maxima. I hope that makes sense. But there is another way to determine which one is the maxima and which one is the minima if you're not drawing it out. So we're going to look at that in just a little bit of time. So since this is a cubic, these maximums and minimums are called local max and local min. Short form, just add local. So pretty cool. It's just a naming convention, because in a quadratic, if you think about it, there's just one. It's either a minima or it's a maxima, like this, right? If this is like a positive parabola, so this is like x squared and this is negative x squared. Okay, so now finding the tangent's equation to the curve. So if we have got a tangent line and we want to find the equation of this tangent line for this curve, how do we do that? So something to remember, the tangent line only touches one point on the curve, and that is the point we're looking at. Cool. So find the equation of the tangent when x is equal to 7 for the curve x squared minus 6x minus 2, and this is basically equal to y. Just so we remember, I'll just make this a bit smaller. Cool. So fx is equal to 2x minus 6 when we differentiate that. So now let's substitute x is equal to 7 into here. So now we put 7 everywhere there was an x, so this becomes 2 times 7 minus 6, which is equal to 14 minus 6, and that is equal to 8. So now we plug in x is equal to 7 into the first equation. We're trying to find the y coordinate over here as well. So the y coordinate over here is going to be, when we plug it back into this equation, we just find the y coordinate, which is, from my calculations, it is 5. And now we find the equation of the tangent at 7, 5. So we're going to use this equation of line, which goes this way. So we've got y minus y1 is equal to mx minus x1. Where does this formula come from? Real quick. So basically, we know that gradient is equal to m, which is equal to, so we denote gradient by m, and that is equal to y2 minus y1 over x2 minus x1. And if we kind of shift things around and we put x on the top, then this becomes y2 minus y1 is equal to mx2 minus x1. And that is basically what we've got over here, except instead of x2 and x1, we've got y and y1. Okay, I'll just rub this out real quick to clear up some space so that it's not too messy. So now we're just going to plug in the value. We know that y1 is equal to 5 from here. We know that x is equal to 7. And we know that m is equal to 8 from when we found out our gradient. So, oh my god, where were we? Here. Cool. So basically this is going to become the equation. We simplify, and this is the equation of the tangent line. Now let me tell you why this is. So since first what we did was to find the x value over here. So we've got the x, and then we found the y value by plugging the x value into the initial equation that we were given, and we found the gradient. So if there is a line that goes through this point and has the same gradient, so this gradient is equal to m, then obviously it's gonna be tangent to this point, all right? Because we know that the gradient at this point is this much, it passes through this point, and that is why that is our tangent line. And that is why we follow this process to come to the equation of the tangent line. Cool. Now, let's get into some turning point stuff. So, this is a quadratic, because it's basically x squared. Over here, this is a cubic, because it's x cubed. And we can see that there are two turning points for cubic, and there is one turning point for a quadratic. So basically, at these points, the gradient is equal to 0. We need to remember this. The gradient is equal to 0 at the turning points. Okay, so let's start with an example question. Calculate the turning point of fx is equal to 4x squared minus plus 16x minus 3. So we're going to differentiate it because we're trying to find the gradient. We're saying that the gradient is equal to 0. So since we know that this is the equation to the gradient, we just need to make this equal to 0, and then we get that x is equal to minus 2. So I'm going to go a little bit faster, but feel free to pause the video and look at my working so that it makes sense to you. I'm just going to go a little bit quickly because this is kind of like a crash course. So now we're just going to simplify everything, and then we get x is equal to minus 2 when our gradient is 0. And since we know that there's a quadratic, there's only one turning point. All right, so we don't have to worry about two x values or anything. So now we plug in x is equal to -2 into our initial equation, and through calculations we will get a y value. So basically we've got an x, we've got a y, and now we've got our coordinates for the turning point. Remember, we found the turning point by saying that our gradient is equal to 0. Okay, turning points over there, the gradient is equal to 0. Now we're going to look at increasing and decreasing functions. There's not a lot more to go, just 2 more topics after this one. So basically, increasing functions means that the gradient is positive, meaning it's increasing like that. Decreasing means that the gradient is negative, which means that it's decreasing like that. As you can see over here, this is negative, this is negative, this is positive. All right, so when it's going up, when it's going towards growth, it's growing, the y value is increasing, then that means that it is positive. Cool. And I'm just going to really quickly go through some graph stuff. So for this is x squared. So this is how quadratics look like. Now, this is just a linear. This is a linear. And linear equations like 4x plus 2, they make lines which look like these over here. Okay, now let's look at x squared. Cool, we looked at x squared, which looks like this. So it's an upward facing parabola, or it's a downward facing. So something you can remember this by is just make a smiley face and see. Oh my god, that's creepy. But basically, make a smiley face, and since it's happy, it's positive, all right? And make a frowning face. Since it's sad, it's negative. So this one is negative x squared, and this is positive x squared, all right? And this is how x cubed looks like. So a cubic. This is a positive one, so we're growing by the end of it. And for a negative one, we're decreasing by the end of it. For x to the power of 4, we've got like a W kind of thing, so W kind of thing. So this is a positive one, this is a negative one, since we're ending up with decrease and we're ending up with positivity on this one. And this is a x to the power of 5. This is obviously a positive one. This is a negative one. This is basically like double cubic, kind of. Because if you look at cubic, it's like this. And then if you add another hump like this, it becomes x to the power of 5. Cool. So now let's do an example question on increasing and decreasing functions. So let's find the decreasing and increasing parts of this equation. Y is equal to x cubed minus 3x squared minus 9x plus 11. Cool. How do we do this? First, we want to find the turning points, because if you look at this, right, if you look at this, at every turning point, the direction of the graph changes. So over here, it's positive. Over here, after the turning point, it's negative. After the turning point over here, it is positive. So that's why we need to find the turning points in order to see what really is happening with the graph. So dy by dx is equal to 3x squared minus 6x minus 9. That is when we differentiate it all. Now we're trying to find the turning point, so we're going to make this equate to 0, and then we're going to factorize it to get x minus 3 and x plus 1 in brackets. So x is either equal to 3 or it's equal to negative 1. So now we plug it back into the first equation, and we get for x is equal to 3, we do our calculations, and then we find out that y is equal to 16. Sorry, y is equal to 16. And then for x is equal to negative 1, when we do our calculations, we get that it's equal to just 16. So our turning points are negative 116 and positive 3, negative 16. So now we're going to go ahead and draw the graph that we had. We don't have to know everything about the graph, but since we know that there's a positive cubic, we know that it's going to look a little bit like this, right? Now we can easily put where the turning points are. So our first one, which is the negative 1, obviously it comes on more this side, so it's going to be first. So since our graph looks like this, the first one is the maxima. And then when we go ahead, we've got this one as our minima, and that is going to be our 3, negative 16 coordinate, this one. So that's why we can see over here that all of this section is going to be positive, all of this section is going to be negative, and this section is going to be positive. So this is going to be increasing, then decreasing, then increasing. All right. So this graph, the increasing parts of it is before negative 1, all of this side, it's gonna increase, okay? And after 3, it's gonna keep increasing. The only part that it decreases for is between negative 1 and 3. So this is how we can write it out. Increasing is when x is less than negative 1 and when x is greater than 3. Decreasing is when x is between negative 1 and 3. And this is how you can write it out. I hope that makes sense. Now let's look at double differentiation rules. Now this is when I said that you don't always have to draw out a graph to determine which is the maxima and which is the minima. So basically, we're going to do double differentiation. So if you've got something like x cubed, fx is equal to x cubed, f dash of x is going to equal to 3x squared, right? So f dash dash of x is that we're going to basically differentiate it again. So we're going to have 6x, because when this comes to the forward, then it becomes minus 1 and this becomes 6x. Okay, cool. That is how double differentiation works. So now, when we double differentiate with the x x coordinate of our turning point, and if it's less than 0, so we've done some substitution over here, and if it's less than 0, this is our maxima. It's a bit opposite for this, so if it's less than 0, then it's the maxima, and if it's greater than 0, then it's minima. Okay, pretty simple. So we need to look at this function or equation, and we're trying to determine the nature of each turning point, whether it is maxima or minima. So we're going to differentiate it. We're going to put it all equal to 0 because we're looking at turning points. And when we factorize it, we get that x is equal to 6 and x is equal to -4. So if you plug in these values into the first one we got, the first one, which is this one, then we're going to get some y values. We've got -334 and we've got +166. So these are our turning points for that equation. So now we need to check the nature. So we're going to double differentiate this. So we've got our double differentiated expression, and now we're going to plug in -4 everywhere there is an x. So now this becomes -24 minus 6, it becomes -30. So this is less than 0, and that's why it's gonna be our maxima. Remember, it's opposite for this. And over here we've got f dash dash 6 is equal to 36 minus 6, which is equal to 30, and this is gonna be our minima because it is more than 0. Okay, again, it's a bit flipped, I get it, but here you can see I've written 6 -334 is our minima, and -4 166 is our maxima. So we can write minima, not minimum, sorry, and this is maxima, not maximum. Okay, and with that, it seems we have come to the end of this part of our crash course. This is basically all you have to know, really. This is all our basic stuff that you need to keep in mind before you're going into more complicated questions, which I will put out maybe 1 or 2 after this, maybe about 3 actually, to just get used to how this is all gonna work, how you can put all of these concepts into use on questions which require you thinking about like more real things, like a pond, for example, or a box. We're trying to find out the maximum volume of a box, so we can use these concepts to find that out, and I will be exploring that in the next video, so stay tuned for that video. Till then, thank you so much for watching. I hope it really made sense. I did go a little bit quickly over most of the things, so if you have got any questions, feel free to put them down below. I might have made a few mistakes, maybe sometimes I might have missed like a number or something somewhere. Please excuse that. I really tried to do this really quickly, so it was a bit rushed, but the concept is there, and that is what I was really trying to explain. So yeah, thank you so much for watching. I hope you have a great day, and I'll see you next time.